Well, I would like to give you a really, really lazy and quick way should you have to model options prices, calculate exotic options, at least Monte Carlo them, or come up with options Greeks beyond your deltas and vegas. So to get started with that, let's just take a look at some options prices. What I did here is I took a snapshot of 9 months out S&P 500 options. I looked at the bid and ask prices because only transactable prices are real to me. It's a very liquid book. We have a lot of observations. And of course, it looks the same for all instruments. So let's convert it to implied volatilities. What we get here is our usual SMRC. So IVOL goes down and down and down, crosses the forward price, goes down further, and at some point it comes back up again. Now, if we want to model that, I would say that unless you're in the market making business, about 4 parameters should be okay to describe those charts that I just showed you with all the hundreds of observations. And I agree with my previous speakers. We should have mean, we should have volatility, standard deviation, we should have some measure of skewness and some measure proportional to kurtosis. The one slightly controversial proposal that I would like to make to you is that we want to have some semblance of power law right tails in our distribution in addition to the more common power law left tails. Let me give you 4 arguments with that and 1 argument why it doesn't work. The 4 arguments why we should have it is that at least for empirical returns, we sure do have heavy right tails. Then there are some securities where the representative investor should dislike price shocks. Energy would be an obvious example, maybe not the S&P 500, or certainly not the S&P 500. We also observed that there is no strike price for which anybody would give us a call option for free, certainly nobody who could pay if it came due. And the option SMRC doesn't really flatten out with increasing tenors as you would expect by the central limit theorem if you did not have extremely high moments at work there. But of course there's a problem, the ultraviolet catastrophe. For those of you from physics, the integral over our expected value blows up to infinity if we have power law right tails in log space. That can't really be because we know the finite forward value. What some people have done is just introduce some arbitrary truncation parameter for the return distribution. The problem is I don't really know how to select the truncation. So a little bit of hand waving, let's do it the really lazy way, and say we don't really care if our PDF integrates up to infinity because it does not do so at any strike price that we can even remotely observe or care about, or maybe even that our computer can numerically do. We just hang up our call prices at the known forward price, then go by Brayton-Litzenberger, so integrate a chosen probability density function twice. Constant of integration is our known forward price. And that way we will get a set of call prices. And should we, for a ridiculously high chosen strike, get to negative call prices, we just set that to 0, which effectively caps the distribution, but we don't really have to care about that mechanism. I know it's hand waving. And lo and behold, there is a suitable probability density function. The SN package has the skew-T distribution, which gives you exactly the 4 parameters magically that we need. Location, stretch, shape, tail heaviness. As special cases, you get student's T, and therefore, as a special case of that, the normal distribution if you're so inclined. Now we can fit that to the options prices that I showed you, trying to minimize bid-ask price violations. And we get this fit here. It doesn't look that bad, does it? For using some prepackaged probability density function, a 1-line function call, and that's really all there is to it. So we're not always within the bid-ask prices, but we're pretty darn close, especially if you say that using 2 instead of 4 parameters, all I could get is the horizontal line from Black-Scholes, which obviously doesn't fit. One problem that I have here is that with my power law tails, with this as with most probability density functions, I'm having the same power law exponent left and right. If you actually look at how returns come in, you probably want to have a somewhat higher exponent on the right tail. That problem causes my skewness to come out a little bit too high when I optimize, and so I get that peak there where I'm not fitting quite as I should. To conclude, let me show you, just for your stock market conversations tonight, what the options markets were implying about where S&P 500 should fall by December on a risk-neutral basis, mind you, not on a subjective basis. And so what's kind of cool here is this enormous amount of skewness and kurtosis that you have in there, with a large probability of markets going up a little bit, significant probability density at S&P 500 being back at 1500, can you imagine? And hardly any density placed by the representative investor at 3000 S&P 500. If you compare that to the log normal distribution, kind of looks cool, I think. And really, to conclude, what can you do with it? You can call Greeks. I would very much like to introduce the name Škoda for the skewness Greek, Kappa for the kurtosis Greek, or you can Monte Carlo it, and in that case, just be careful that your forward value comes out, because by design, the tails are fat. That's the entire point of it. Thank you.
Okay. Hi, everybody. My name is Shuang Zhou. I'm here to represent my research group to present our recently new work, a non-parametric estimate of the risk-neutral density and its applications. So you can tell, our purpose, is we propose one piecewise constant non-parametric approach in estimating the risk-neutral distribution. So basically, we are trying to divide the domain of the risk-neutral density by Q distinct knots. Those Q distinct knots representing all the distinct available strike log prices. And now you can, and also for each interval between two adjacent knots, we represent the value by a parameter A. So in such a way, we result in having Q plus 1 parameters. And since we are trying to estimate one density, so we need to guarantee the non-negativity and the unit integration. And the optimized objective function in terms of the Q plus 1 parameters is as following. It is actually, we are trying to minimize the sum of the relative error of our predicted option prices versus the market option prices. And here I'm presenting our work, our result in, for the prediction error for all the options under our weighted least square approach. I'm sorry, this optimization function, we call it weighted least square approach. And you can tell that it's a pretty good result with the average relative error for all out-of-the-money options reaching as low as 2.4%. And the lowest relative error for in-the-money options reaching for 1.9%. So, and also we compare our results with the literal approaches. Here, we compare our result on 200 randomly selected data pairs with the literature approach, cubic spline methods. It's not difficult to see that our approach completely beat the literal approach. Like just for example, for the options with 17 to 31 days to expire, our relative error for out-of-the-money options and in-the-money options are within 3%. And no, I'm sorry, are within 9%. And but for the cubic spline approach, the lowest error for them is 15%. So it's a completely winning approach. And now I introduce some applications of our risk-neutral density estimate. One of the approaches to discover to recover risk-neutral density. And it is very consistent with the common guess of the risk-neutral density shape. So our function is displayed as this. You just need to input the option, the current option price list, the strike price list, the option type list, and the risk-neutral rate, and the time to expiration. And it will give you the risk-neutral density and parameters and all the corresponding knots. And another application is to unveil the investment opportunities. And we will be able to recognize some options on the markets that are under or above estimated and explore profitable investment opportunities for the investors. And also we write the R function as follows. Similarly, you just input the option information and you will get the confidence interval for each option price. And for those option prices falling out of the confidence interval is where we need to further investigate into. Okay, so the last but not the least important application is to provide a fair price for any derivative with the same time to expiration, say options. Similarly, we also wrote the R function. Since I'm running out of time, I just want to show you here. This is our option price estimation. The red one is the market price, and the blue one is our predict price. As you can tell, they are pretty close. And also, if you are further interested, you can talk. If you are interested, you can talk to me about a variance swap, which is also a major application of our risk-neutral density estimation. Okay, thank you.
Okay. So I try to keep it simple and short. So this is like a sort of optimization problem with two constraints. So I'm going to talk about hidden Markov models, and I'll apply it to volatility. Page down, okay. So this is a question I hear pretty frequently in our training desk. So how's market today, yeah? So you get many possible answers. I mean, I try to say that, okay, we are having a bullish day or a bearish day, and if we are doing risk, some may answer, okay, today is volatility is low or it's high, and if you like behavioral finance, you may say, okay, we are in a risk-on period, or we are in a risk-off period. So these are just different answers, but they have something in common, yeah? Which is markets don't behave exactly the same way every single day. So, I mean, markets have states, yeah, but they are hidden. You can say the price is hot, a stock is hot, but you can measure its temperature, yeah? You need a proxy. I mean, you can observe the state of the market, but you can do inference based on the variable you actually observe, yeah? So one way to model this is using hidden Markov models, which is just two models, one atop the other. We have a state model, which is just a discrete Markov change, which is hidden. And we have an observation model, which is just your pricing model, your risk model, or whatever model you need for your observations. Of course, as Bob said, no model is perfect. We are just trying to get some approximation to reality, but don't expect this model to make magic, right? So I'll just keep this. Let's set up a model. Say we wanted to model volatility, yeah? We grab some data, thanks to Joshua, using QuantMod. And we just, to try to keep things easy, we'll use a binary state model, just a first order Markov chain. And we use just a Garch 1-1 model for volatility, yeah? So we estimate two processes. We observe one price, but we estimate two processes for volatility. One is a high volatility process, and one is a low volatility process. And depending on the return we observe, which is our only observation, we'll try to map it to a space, and we'll try to guess to make inference on what's the probability that the price for today is linked to the high volatility process or the low volatility process. Of course, the closer the returns to zeros, then the low returns, of course, then you are more confident that you are in the low volatility space, right? Or the low volatility model. So we'll run this for 2 stocks independently. And we'll see that if the stocks are in the same industry, the probability that one stock is in one process is somehow correlated with the volatility that other stock is in the same process. I mean, if Ford is having, say, a low volatility day, it's more likely that GM is having a low volatility day too. But we are running the model independently, so this is data speaking to us. And I pick, for example, in the to the right, I pick Ford and I pick Airbus, and you see the correlation is lower because they are not in the same industry, right? And it makes sense. So, what's the takeaway for this? First, these states are hidden, yeah? So this is unsupervised learning, yeah? But they are meaningful. I mean, I heard a lot of times that people think that hidden states are somehow obscure. Yeah, that is sort of esoteric. But no, they are meaningful. They are subject to useful domain knowledge. In this case, we can map it to high and low volatility or to a bearish or bullish market, right? Belief states across assets are correlated, yeah? And the correlation is stronger when the stocks are in the same industry. So similar business model or similar exposure to, say, some factors. In this case, I just wrote microeconomic factors, but this could be any pricing factor, right? So the idea is, if I run the model to 2 independently stocks and they are correlated, so there is more information we can get from the same data, yeah? And if they are correlated, maybe we can model some hierarchical hidden Markov model that would link the correlation in this state probability, the belief probabilities. So, for example, a global portfolio could be somehow mapped into a country state, and then between the countries we could have industry state, and then each stock could have its own state. So this is what I'm trying to do in my Google Summer of Code project this year. So if you find this is interesting, you can just go to my Hitbag account, fork the package, toy with it. There is also a notebook, an art notebook for you to play with the model I made for data. So you can always fork, and PR are welcome. And if you have questions, you can ask later in the dinner. Thank you.
Hi everyone. So this is a joint work with Carol Bernard and Steven Van de Vel from VUB. So we try to address the following problem, which is kind of important in finance. So suppose we observe marginal distribution for D stocks and also distribution for their sum, some weighted sum. And we would like to learn something about their dependence. We don't know the joint distribution, but we would like to know how the stocks interact between themselves. So for example, we could use option data, and this is similar to the 2 talks before, and we could extract risk-neutral densities for, let's say, 30 components of Dow Jones and for Dow Jones itself. And again, we want to learn something about dependent structure. So there are many important applications in finance, but this is a hard problem. And what we try to do in this paper, we want to solve it with the so-called block rearrangement algorithm. And what we find that this approach works quite well, and importantly, even though there are infinitely many solutions, typically, BRA tends to find a specific solution, and this solution is actually economically quite sensible because it exhibits maximum entropy. So general setup is the following. We have D random variables. Again, think about stock prices. And we discretize them. So we have n equally probable realizations. We put them in matrix. So each column is a stock. And then we try to rearrange columns. And the idea is that we allow to rearrange columns, and we try to make sum in each row as constant as possible. Now, we can try to solve this problem with brute force, but this is NP-hard problem, and the number of possible rearrangements is enormous. Fortunately, there is a very effective and simple and very fast heuristic approach which was recently developed. It's called rearrangement algorithm. So the basic idea is simple. You pick a column and you sort it so it is anti-monotonic with respect to sum of the remaining rows. If you keep doing this by picking different columns, eventually the algorithm will converge, and after each step, the variance of the row sums keeps going down, and because it's bounded from below, the convergence will happen. So block rearrangement algorithm is improvement or generalization. Now instead of one column, we do partition into 2 blocks, and sum in the first block is made anti-monotonic with respect to sum of the second block. So if number of stocks is relatively small, we could go loop over all possible partitions. When D is large, we would do random search. Okay, so how do we propose to infer dependence? So we'll have D columns for D stocks, and we'll add one more column, which will be negative of the sum. So this is like negative for the index. So now we apply BRA, and the result will be row sums equal to 0, and this is when candidate compatible dependence has been found. So let me just show you a couple of illustrations. I will start with Gaussian case, and basically we'll have from 3 to 10 stocks, we'll have discretization from 1,000 to 10,000. We'll run BRA 500 times, and let me just show the picture. So on the left panel, there is this gray ellipse, looks like egg, but it represents a set of all possible solutions. And there are 500 blue dots. Each dot represents one run of BRA, and they all clustered around the red star. So the red star, this is one particular implied dependence which corresponds to maximum entropy. And what is maximum entropy in this case? Well, it's a dependence which has Gaussian cupola, and it has correlation matrix with maximum possible determinant for given marginals. So you can see that all 500 dots kind of clustered around this point. So now it's the same example, but I increased discretization from 1,000 to 10,000, so now they're even more clustered. And 1 minute, okay. I'm not going to keep streak alive. So I'm skipping all of this. I will just show another illustration. So suppose I start with the solution, but it's not a maximum entropy solution. It's shown by green dot. And I will make a tiny perturbation. So out of 1,000 rows, I will flip 2 randomly, and then run BRA. And what you can see that even with small perturbation, I start to get pulled back to the stable maximum entropy solution. When I start to increase resolution, this pull becomes stronger and stronger. So with 10,000 discretization points, again, I'm back to the stable maximum entropy equilibrium or solution. To conclude, the similar results we showed also for non-Gaussian distribution. This maximum entropy property holds only for block rearrangement algorithm, but not for the standard one. There are a number of important applications in finance, like pricing multivariate options, basket, spread, etc. We can construct forward-looking measures of the tail risk, implied dependence. We can estimate down and up correlation, and we could also use it for portfolio optimization. And the paper is available online on SSRN.
Hi everyone. Today I'll be talking about risk and performance measure standard errors. This is joint work with my advisor, Professor Doug Martin. So risk and performance measures are very widely used in finance, but the true values of these measures are almost never known. So we have to estimate these true values from data. And it's very important to know that the estimators are themselves random variables, and they have two important properties. The first property is called bias, which is the difference between the expectation of the estimator and the true value. This is well understood in finance, as most of the commonly used estimators are either low biased or unbiased. And the second property is the variance, which is a measure of the dispersion of the estimators. And this is much less well understood and is often ignored in finance, as far as I know. So here's a diagram showing the impact of variance on your estimator. So in these diagrams, the red circle in the center is the true value, and the blue dots are the sample estimates of the true value. So on the left-hand side, it's showing the low variance situation. You can see that most of these blue dots are sort of closely clustered around the expectation, which is the ideal case, but unfortunately, it is not always the case in practice. Sometimes the high variance situation, which is shown on the right-hand side, appears in our application. In this case, the blue dots are very widely spread across the board. And if we have a relatively small sample size, then our sample estimates may as well be those blue dots that are fairly far away from the center. So that is actually the worst case scenario for us, especially decisions about asset allocations are being made on the assumption that our estimates is very close to the true value. So hopefully I have convinced you guys that at least knowing the standard error is useful. Then the question is, how do we compute these standard errors? Actually, we wrote an R package that does exactly that, but I won't dive into the details of the math and statistics. Instead, I will show just a couple of examples. Here is an example using the hedge fund returns data. We picked 4 hedge fund styles, and we compute the sample expected shortfall with tail probability of 10%. And then we use our proposed new method, which is indicated by IF, which is influence function approach. And then we compare it with the bootstrapping method, which is implicated by this boot. And then the IID means we're assuming the data is IID distributed, and the core means we're assuming the data is serially correlated. So there are 2 takeaways from this table. The first takeaway is that the IF approach results are relatively close to the boot approach results. So that's very assuring, showing that we're doing things correctly. And then the second takeaway is that serial correlation actually has a huge impact on the standard error. So if you look at the first row, which is the results for the convertible arbitrage time series, the IID assumption actually significantly underestimates the standard error, which gives you a false sense of security that you're having a relatively accurate estimate of the true expected shortfall. While for the other 3 rows, we're getting almost similar results across the board, which can be further supported by the fact that the time series for the other 3 hedge funds are not serially correlated. And then I will show another Monte Carlo simulation that compares the accuracy of our proposed approach compared with the other 2 state-of-the-practice approaches. What we did is we simulate 5,000 AR1 processes with different serial correlation coefficients, which is shown on the y-axis. And then we compute the percentage difference of the estimated standard errors of these methods with the true standard error. And that percentage difference is shown on the x-axis. And we did this for Sortino ratio and the expected shortfall. And you can see from the results that the red triangles, which represents the percentage error of our method, is actually almost always outperforming our competitors for the serial correlation coefficient ranging from 0 to 0.5. So that is what we consider like the practical serial correlation you will see in most of the financial time series data. So we're pretty happy to see these results, even though they're sort of preliminary. So in summary, hopefully we have made the argument that it's at least useful to look at the standard error of your risk and performance measure estimators, and we have introduced a new and competitive way to compute those standard errors. And also we have done most of the work already, and the R package is available at this GitHub repository. And in this summer's Google Summer of Code, we will be working on an efficient implementation of the algorithm with our C++. Thank you. That's all.